formula volt-amperes divided by the quantity of 240 volts times 1.73 is the correct method to calculate the total amperage in a three-phase system. The value 1.73 represents the square root of 3, a fundamental constant in three-phase power calculations. To elaborate further, three-phase power systems utilize three conductors to transmit electrical power, unlike single-phase systems that use two conductors. This difference in conductor usage contributes to the enhanced efficiency of three-phase power distribution. Consequently, three-phase power is frequently adopted in commercial and industrial settings where substantial power demands exist. The absence of neutral current in balanced three-phase power systems leads to reduction in the total amperage supplied by a three-phase source compared to a single-phase source delivering the same power. Specifically, the amperage in a three-phase system will be approximately 1.73 times less than in a single-phase system for an equivalent power output. To illustrate this difference, consider a 100 kVA single-phase source. To determine the amperage, we divide the volt-ampere rating by the voltage. If we assume a voltage of 240 volts, the current would be 100,000 volt-amperes divided by 240 volts, which results in approximately 416.67 amps. However, because single-phase residential services are divided into two legs, each leg carries half of the total load, or 208.33 amps per leg. Now let's consider a 100 kVA three-phase source at 240 volts. The calculation for amperage is volt-amperes divided by the quantity of voltage times the square root of 3, or 100,000 volt-amperes divided by the quantity of 240 volts times 1.73. This yields approximately 240.96 amps. The difference between the single-phase and three-phase amperages for the same kVA load is significant, highlighting the efficiency gains achieved with three-phase power distribution. In three-phase systems, the power is evenly distributed across the three phases, resulting in a smoother and more efficient power delivery. This is particularly advantageous for heavy-duty motors and industrial equipment, which often require a consistent and reliable power supply. Furthermore, three-phase power can reduce conductor sizes and associated costs compared to single-phase systems for the same power requirements. This is because the current is distributed across three conductors instead of two, allowing for smaller gauge wires to be used. In summary, to calculate the total amperage in a condo building supplied with 120/240 volt three-phase power, the formula volt-amperes divided by the quantity of 240 volts times 1.73 should be used. This formula accurately accounts for the characteristics of three-phase power distribution, including the absence of neutral current and the efficient use of three conductors. The square root of 3 factor is crucial for determining the correct amperage in three-phase systems, and understanding its significance is essential for accurate electrical calculations. When working with electrical systems, it's always advisable to consult with a qualified electrician or engineer to ensure safety and compliance with relevant codes and standards. Precise load calculations are critical to ensure that the electrical system can handle the anticipated demand without overloading. It is important to note that the actual amperage in a three-phase system may vary slightly due to factors such as voltage imbalances, harmonic distortion, and nonlinear loads. These factors can affect the accuracy of the calculated amperage and should be considered in more detailed analyses. Voltage imbalances occur when the voltages on the three phases are not equal, which can lead to increased current in one or more phases. Harmonic distortion is caused by nonlinear loads, such as electronic devices, which draw current in a non-sinusoidal waveform. These harmonics can increase the overall current and stress the electrical system. Nonlinear loads, such as variable frequency drives and LED lighting, can also contribute to inaccuracies in amperage calculations if not properly accounted for. These types of loads can draw current in a way that distorts the voltage waveform, leading to higher peak currents and a lower power factor. The power factor is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all of the power is being used to perform work, while a power factor less than 1 indicates that some of the power is being wasted. Nonlinear loads can lower the power factor, which can increase the overall current and stress the electrical system. In practical applications, it is important to measure the actual current in each phase of the three-phase system using an ammeter to verify the calculated amperage and identify any potential issues. Regular monitoring of the current and voltage in a three-phase system can help to detect problems early and prevent equipment damage or power outages. Furthermore, it is essential to ensure that all electrical equipment and wiring are properly sized and installed according to applicable electrical codes and standards. Overloaded circuits can cause overheating, insulation damage, and even fires. Therefore, it is crucial to perform thorough load calculations and select appropriate circuit breakers and wire sizes. In addition to the fundamental formula for calculating amperage in a three-phase system, there are other factors that can influence the total amperage drawn by a building. These factors include the types of loads connected to the system, the diversity of the loads, and the operating conditions of the loads. Types of loads connected to the system can significantly affect the total amperage. For example, resistive loads such as electric heaters and incandescent lighting draw a constant current at a given voltage. Inductive loads such as motors and transformers draw a current that lags behind the voltage, which can lower the power factor and increase the overall current. Capacitive loads such as capacitors and some electronic devices draw a current that leads the voltage, which can improve the power factor but also introduce other challenges. The diversity of the load refers to the fact that not all loads in a building will be operating at their maximum capacity simultaneously. For example, the air conditioning system may only be running at full capacity during the hottest hours of the day, while other loads such as lighting and computers may be running at a constant level. The diversity factor is a measure of how much the total load is reduced due to the fact that not all loads are operating at their maximum capacity simultaneously. The operating conditions of the loads can also affect the total amperage. For example, the current drawn by a motor will vary depending on the load that the motor is driving. A motor that is driving a heavy load will draw more current than a motor that is driving a light load. Similarly, the current drawn by a lighting system will vary depending on the ambient light level and the settings of any dimming controls. In order to accurately calculate the total amperage drawn by a building, it is important to consider all of these factors. This may involve performing a detailed load analysis, which includes identifying all of the loads connected to the system, estimating their operating conditions, and applying appropriate diversity factors. In some cases, it may also be necessary to use specialized software or measurement equipment to accurately determine the total amperage. The National Electrical Code, or NEC, provides guidelines and requirements for electrical installations, including load calculations. NEC Article 220 covers branch circuit, feeder, and service calculations. This article provides methods for calculating the minimum size of conductors and overcurrent protection devices required for various types of loads. For example, NEC Section 220.12 specifies the lighting load requirements for different types of occupancies. This section requires a minimum lighting load of 3 volt-amperes per square foot for dwelling units and 3.5 volt-amperes per square foot for office buildings. NEC Section 220.14 provides requirements for receptacle outlets, appliance loads, and motor loads. This section specifies the minimum load requirements for these types of loads and provides guidance on how to calculate the total load for a circuit. NEC Section 220.82 provides an optional method for calculating the feeder and service loads for dwelling units. This method allows for a reduction in the total load based on the diversity of the loads. NEC Section 220.87 provides an optional method for calculating the feeder and service loads for existing installations. This method allows for a reduction in the total load based on the actual demand of the installation. It is important to consult the latest edition of the NEC and any applicable local codes and standards when performing electrical load calculations. These codes and standards provide detailed requirements for electrical installations and are intended to ensure the safety of people and property. Electrical calculations and three-phase systems can appear daunting, therefore consulting with a qualified professional is advised, as mentioned. These professionals can perform accurate load calculations, ensure compliance with codes, and assist in safe and effective electrical distribution design. In conclusion, determining total amperage in 120/240 volt three-phase systems involves understanding the relationship between volt-amperes, voltage, and the square root of 3. Factors such as load types, diversity, and operating conditions also influence this calculation. Furthermore, adherence to NEC guidelines and consulting with qualified professionals are essential for safe and efficient electrical installations.